All right, welcome. Today we're going to jump into something that's really at the heart of algebra, classifying real numbers. Think of it like learning the secret family tree of every number you've ever met. And trust me, understanding this is going to make everything else so much easier. So, let's dive in.
I love this quote from Baker's math class because it just hits the nail on the head. Not all numbers are created equal. That one idea is the key to this whole thing. It tells us that numbers have different personalities, different jobs, and they belong to different groups.
So, to get a handle on all of this, we're going to use a really helpful metaphor, a giant family tree. Every single number has its own spot, its own relatives, and a specific household it belongs to. Framing it this way is going to help us see how everything connects. So here's our game plan. We'll start with the core family. Then we'll branch out to some of the relatives, and we'll even meet the mysterious family outlier. After that, we'll get some practice placing numbers in the tree. And finally, we'll see why this whole family tree thing actually matters outside of your math class.
Okay, so think about any family photo, right? There's always that core group right in the middle. Well, in the world of numbers, that's where we're going to start. These are the most basic, fundamental numbers, the ones you've probably known your whole life.
Right at the very bottom of our family tree, we have the natural numbers. Think of them as the toddlers of the family. They're the first ones you ever learned. These are your classic positive counting numbers.
1, 2, 3, 100, 500, and on forever. Basically, if you can use it to count stuff, it's a natural number. Simple as that.
Now, let's expand that household just a little bit. The whole numbers include every single one of the natural numbers, but they invite one really important new member to the family, 0. And that's a big deal. Suddenly, the idea of nothing gets a seat at the table. So you can see the natural numbers are a part of the bigger group of whole numbers.
But the family photo gets bigger still with the integers. This is where we bring in the idea of opposites. For every positive number, we now have its negative twin. They're like the mirror images in the family.
So now our family line includes not just 1, 2, and 3, but also -1, -2, and -3, stretching out to infinity in both directions. This means the whole numbers we just talked about fit perfectly inside this even bigger family of integers.
All right, we've met the immediate family. Now it's time to meet the extended relatives. And let me tell you, this is a much bigger, much more diverse group.
These are the rational numbers, and the clue is right there in the name. They can all be written as a ratio, which is just a fraction. So the big takeaway is, if you can write a number as one integer over another, boom, it's in the rational family.
Now this is where it gets interesting. This group obviously includes fractions like 3/4, but here's the crucial part. Every integer we just met is also rational. Why? Because you can write any integer like -2 as a fraction, -2 over 1. This family also covers decimals that stop, like 0.75, and even decimals that go on forever in a nice repeating pattern. See? Our family portrait just got way bigger.
You know how every family has that one mysterious, unpredictable member who kind of marches to the beat of their own drum? Well, in the number family, that is absolutely the irrational number.
So what's the test? How do you tell them apart? It all comes down to their decimal form. Rational numbers are predictable, right? Their decimals either end neatly or they repeat in a clean pattern. But irrationals? They're wild. Their decimals go on forever and ever with no pattern at all. The famous number pi is the perfect example of this beautiful, chaotic mess.
Okay, so we've met all the different family members. Now it's time to put our new skills to the test. We're going to take a few numbers and figure out exactly where they belong on the family tree.
Let's start with a nice, easy one, the number 7. Okay, first question. Is it a counting number? Yep, so it's natural. And since all naturals are also whole numbers, it's a whole number. And because all whole numbers are integers, it's also an integer. And can we write it as a fraction? For sure, 7 over 1. So it's also rational. See how it belongs to every single one of those core groups?
Okay, how about a trickier one, like -3/5? Well, it's not a counting number, so it's not natural or whole. It's not a whole number or its opposite, so it's not an integer. But is it a ratio of two integers? Absolutely. It's already in fraction form. That makes it a solid member of the rational family. So it's not in that core household, but it has a clear spot with the extended relatives.
Now let's tackle a really common stumbling block, square roots. It's so tempting to see that little symbol and just immediately think irrational. But is that always true? Let's put it to the test with the square root of 9.
Now, the first rule of classifying numbers is you have to simplify first. The square root of 9 is just 3. And we already know that 3 is natural, whole, integer, and rational. So the square root of 9 is actually a totally rational member of the family.
But what about something like the square root of 7? Well, 7 isn't a perfect square. If you punch that into your calculator, you get this long, crazy decimal that never ever ends and never repeats. That, right there, is the classic signature of our mysterious cousin, the irrational number.
Okay, so we've spent all this time sorting numbers into their little boxes. But you might be thinking, who cares? Why does this even matter? Well, let's connect this back to the real world, because it absolutely does.
First, let's just quickly recap the big structure we've uncovered. This table shows that nesting pattern perfectly. The natural numbers live inside the whole numbers, which live inside the integers, which all live inside the rational numbers. It's just like those Russian nesting dolls, where each one fits perfectly inside the next.
And this structure is incredibly important. In computer science, choosing the right number type, telling a program you're using an integer versus a decimal or a float, totally changes how the program works. It affects speed, memory, and accuracy. And in finance, oh man, banks rely on the predictability of rational numbers because tiny rounding errors from irrationals could add up to millions of dollars lost over time.
So we've mapped out the whole real number family. We've seen how each group fits inside the next, with those wild irrationals living on their own separate branch. Understanding this is the foundation of so much of algebra. But it also makes you wonder, doesn't it? If this is just one branch of the mathematical family tree, what other strange and amazing relatives are still out there waiting for us to discover them?